Hello, I'm Katie, and welcome to Introduction to Imaging. Just as the title says, I'm going to be giving you all the information you need to start imaging your data. So far, you've learned about radial interferometry, and you've learned the steps to calibrate your data, but now we're going to actually turn the calibrated visibilities into an image. So I'm sure in your previous talks, you've touched upon the term visibilities. Well, I'm going to go over them again because this concept is important for imaging. So the complex visibility function, which is our V with units UV, is effectively the 2D Fourier transform of what the emission is on the plane of the sky. So there are certain conditions where this simple version is not acceptable, but for the purpose of the imaging that you will be doing at first, we will assume that it is. We're going to assume we're imaging a small field of view. So I'm not going to go into the full derivation of the Fourier transform because that would take me a really long time, but I will explain the components of the equation. So if you look at the figure on the left, you'll see the two element interferometer on the ground. So there are two coordinates, this U and V. So U points to the east and V points to the north. So in the sky plane, the intensity distribution is represented by this term TLM. Sometimes T is an I or maybe another letter, but to make it simpler on the screen, I made it a T. So L and M are angles on the plane tangent to the curved sky. So you have this plane tangent to the curve. So both formulas are double integrals. So the sky distribution is integrated over the angles DL, DM, whereas your visibilities also are integrated and you have points DU, DV. All right, I think I said that wrong. So your sky distribution is integrated over the angles and you have DL, DM, or points DU, DV. So you have the term e to the 2 pi I, which is just a series of sines and cosines. So you have a shorthand notation, which is here at the bottom. And this is just a simpler way to write the Fourier transform. The Fourier transforms can go both ways. So if you take the Fourier transform of one, you can take the Fourier transform of the other and you get each other. So if you know one side, you can get the other side. So we just jumped into Fourier transforms, but we want to understand them a bit more. So we want to know how the Fourier transform can help us turn visibilities into an image. So the Fourier theory states that any well-behaved signal, which includes images, can be expressed as a sum of sinusoids. So if it didn't include images, we'd be very lost and we wouldn't know what to do. Because the Fourier transform is a mathematical tool that we can use to decompose the signal into its sinusoidal components. Remembering that the equation in the last slide, we know the Fourier transform has some information that tells us about the strength and the place of the original signal. So visibilities are complex quantities. They include both real and imaginary parts, but you can also call this your amplitude and phase parts. So before we do that, I want to stress that each UV point does not correspond to a single point in the sky brightness. So it's not a one-to-one. Because you have a sinusoidal phase term, the UV point includes information on the sky brightness everywhere in the field. So here's a small example I put of a Fourier transform of an image. So we have a robin and the Fourier robin. So here's another example of a Fourier transform of an image. Here's the cat, which represents the sky brightness distribution, T. So if you Fourier transform the image of the cat, you get visibility information at a bunch of UV points. So you can break it up into amplitude. So you can look at this image, you have amplitude, and you can break it up into a phase component. I labeled on the plot for the amplitude, at least, the UV axis, where the amplitude at the center, you can see it's very, very bright compared to the other parts. So amplitude tells us how much of a certain spatial frequency there is, while phase tells us where the spatial frequency component is located. Without the phase component, the image would not be well constructed because we wouldn't know where to put the information or the amplitude information. So let's look at a few more examples here. So you can take the delta function on the left. So you have this delta function. So the delta function is the narrowest function you can really have. So a Fourier transform of the bright peak at the center of your narrowest function results in a constant in the visibility. So you can see every point in the visibility has the same amplitude. In the picture on the right, we have a Gaussian image. So the Gaussian is spread out more than the delta function. You can see. So if you do a Fourier transform of the image, it results in a larger kind of sphere. It's spread out. Remember that Fourier transform, if you go one way, you can go the other way. So as you can see, if you start off with small features, narrow features like the delta function and the small Gaussian, you get the result of a broad, wide feature. So if you go the other way, you have these broad features, you can Fourier transform them into narrow features. So 2 points to remember. The first being that if we set the UV to 0, 0, which is our origin, I've labeled it on the amplitude plot. That's the point where we get the value of our total flux density. So when you observe, you try to get the target in the center of the field. The second point, because the sky brightness is real, we get that the visibility at the visibility point minus U minus V is equal to the visibility point at positive U, positive V. So you get 2 points for one measurement. This is really helpful when you're trying to get as many points as possible in your UV plane. Because of how telescopes and array are set up, you will never fully sample the UV plane. Even if you could place antennas to collect at every single UV data point, you would still lose some flagging, but you'll never be able to place the antennas to collect at every single UV point. So this leaves us with information gaps in the UV plane, with only particular places sampled. So if we assign a sampling function, S, to include in our visibility function, so for every point that has data, we can assign S equals 1. And every point that doesn't have data, we can say S equals 0. So you can see at the bottom equation, it shows the sky brightness equal to the visibility function multiplied by the sampling function. You'll notice though, our sky brightness has an extra D in the superscript of the T. So I'll kind of go into what D means next. The Fourier transform of the visibility function with our sampled visibilities yields the true sky brightness convolved with the point spread function. So T, which is our true sky brightness, we're going to convolve it with B, which is our point spread function. So B we also call as the dirty B. So because the point spread function is called the dirty beam at times, we denote the T, D, to be the dirty image. So B is just the Fourier transform of the sampling function. So here we have images to show what all those equations mean and like what the result of those equations is. So on the top left, we have a sampling function. So the UV plane, where there are data points, s equals 1, and the parts that have no data points, s equals 0. So if you Fourier transform the sampling function, you get the dirty beam, which is on the top right. So if you convolve the dirty beam with the sky brightness, right here in the bottom right, it'll produce, bottom left, the dirty image. So as I said in the previous slide, you will not get data on every UV point, no matter how hard you try to design a perfect array or observation. So the samples of the visibilities are limited by the number of antennas and by Earth sky geometry. So look at the UV samples in the UV plane in the image on the left. So you have this outer boundary, which is at the edge of the gray. You have long baselines that fill in the data further out. These long baselines also limit the size of the object you can see. There will be no information on targets with a size smaller than the resolution limit of the telescope. So interferometers typically have an inner hole right at the center, which is the little white area at the center, right here. So antennas can only be so close without blocking each other. And this has a similar problem as like the outer limit. So the array cannot view features larger than the resolution limit of the shortest baselines. So any structure that's bigger than that will be invisible to the interferometer. The other problem you'll have with collecting UV data is the irregular coverage based on spacing between the antennas. So occasionally you can have one telescope that may be out of commission, which restricts your UV coverage even more. Or you can have a telescope that was terrible during the entire observation and you need to flag that every baseline with that antenna. We cannot get information on data if it hasn't been observed. So these cat photos have been included. So they're showing you the effect of using data at different spatial frequencies. So in the top left image, you have a high spatial filter, which has removed the inner region. So if you only have the low spatial frequencies measured, you're going to get, when you Fourier transform it, an image of a cat, but the cat is quite faint, but you can see the resolution is good. You can see small detail in the cat's face and structure. The total flux is gone, but small features are now visible. So in the right cat image, the opposite has been done. So the low spatial frequencies have been removed, leaving only the high spatial frequencies. So our resolution is now so great, but we have more flux. So you can't see as much detail, but you definitely have more flux. So it results in a blurry cat image. So I've talked a lot about the Fourier transform, but not a lot about how it's done. Obviously, we're not doing a Fourier transform on millions of data points by hand. So nearly all of the structure we use for imaging uses something called a fast Fourier transform algorithm. So the fast Fourier transform algorithm, as the name suggests, is faster and much more simpler than a direct Fourier transform. So if we were to do a Fourier transform to every point, it absolutely would take a very long time. The problem, though, with a fast Fourier transform is that the data needs to come on a regularly spaced grid. So radio visibilities may be regularly spaced in time and frequency, but they are certainly not evenly spaced in the UV plane. So if you think back to the grid of UV points that we had, and how there's gaps in the outer ones, especially in the outer measurements. To fix this, we have to grid the visibilities. So gridding resamples the visibilities into a grid. So like the image here, you can imagine setting a grid over the UV plane to cover the visibilities. So typically a convolution method is used to minimize smoothing and aliasing. So aliasing is basically where your images start to bleed over from a map, and you can get sources showing up in wrong spots, or basically a repetition of patterns of sorts. So our gridding function is then gridded visibilities Fourier transformed into our dirty image. So it becomes our dirty image convolved with the gridding function. So by now you should have been introduced to CASA. So you use CASA to calibrate and inspect your data, your visibilities. CASA can also be used to produce images. So there are two main imaging tasks in CASA, and they are clean and T-clean. So in many ways, they are used the same way with many of the same parameters. There are only minor differences that maybe only matter for more advanced imaging that you won't need today. So clean was the older task, where T-clean became the new updated version. To get a basic image, you must tell your program, you need to give it vis equals your measurement set name. You need to give your image an image name. So image name equals whatever you want to call it. So the size of the image in pixels. So you want you don't want too big of an image if you don't have to, because it can cost you computation time if it's too large. But equally, you don't want it too small. You need to set a cell size. So the cell size is the angular extent of a pixel. A good approximation is lambda over 3b. So lambda is your highest frequency, and b is your longest baseline. In practice, you could determine your point spread function and make sure you have a cell size where 3 to 5 pixels fit across the main lobe of the dirty beam. So you don't want any less than that. So going back to image size too, you want an initial image size matching the primary beam to start. So if you do that, you can identify bright sources that may cause complications in your image. And we'll discuss later on what the effects of these additional bright sources can cause or can have on your image. So how does CASA actually make an image? There's a reason the task is called clean or T-clean. Most imaging algorithms use the original clean algorithm or some modified version. So clean works like this. First, CASA initializes, it creates an image and an empty clean component list. It then searches the residual map for the brightest point. So when it finds the brightest point, it'll multiply this value to some gain factor and subtract it from the residual map. The amplitude and location of the point where the peak was is added to the clean component list. You then repeat the whole process until some criteria that you've told the program has to stop when it reaches has been met. So once the program stops searching, the clean component then list is convolved with an estimate of the main lobe of the dirty beam. So it's often an elliptical Gaussian, and the residual map is added back in to make the final clean image. So here's an example to show the difference between the dirty image and the restored clean beam. So it's difficult to do science with the dirty image because there's a lot of noise surrounding the real emission. So you can imagine the fainter emission in the image might be more difficult to separate from your noise. So I mentioned earlier that the clean algorithm stops when it reaches some criteria that we set. So how do we know what stopping threshold to tell CASA? Well, there's different things to consider. You can have either a noise limited map or a dynamic range limited map. So for a noise limited map, the residual map peak is less than some multiple of the RMS noise. For a dynamic range limited map, the residual map will have a peak less than some fraction of the dirty map. So you can also set the max number of clean components. And if you've hit that number, the program will automatically stop. This is the parameter n-iter in clean. So another question you may have had, I've mentioned that during the process of clean, it finds the peak and multiplies by some gain factor. So what should this gain factor be? Typically, this is set to 0.1 to 0.3. But if you have smoother emissions set, you can set the gain to 0.05. But when in doubt, 0.1 is acceptable, and just use that if you're not sure. So even when using a fast Fourier transform, you can imagine that producing an image every time the algorithm finds a peak can be painfully long. So the clean program has two cycles. There is the minor cycle and the major cycle. The minor cycle subtracts sub-images of the dirty beam. The major cycle does Fourier transform of the residual map and subtracts the peak multiplied by the gain factor. So if you know where the real emission is in your map, you can set clean boxes, and the clean boxes are to be placed around the source so that you can tell the program where to look for the peak. You don't necessarily need to set boxes, but it's a good idea because it can help speed up the process. Instead of having to look in an entire field where there's no emission, you tell it where it is. But you should take caution because when you're setting boxes, although you can't remove any real emission if you don't, you can introduce artificial structures if you've included non-real emission. The telescope array observes the source with data at various UV points. So remember the sampling function we discussed in slide 8. So each data point is assigned a weight. So that is how much influence each visibility has over the image structure. So remember that the resolution is dependent on the wavelength and the baseline length. So if we change where the data is strongly placed, we can change our dirty beam shape. To do so, the sampling function we discussed in slide 8, again, remember we assign s equals 1 to visibility points that have data and s equals 0 to points where there is no data. That sampling function needs to be modified, adding in the other term, W, where W is the weight. So we can adjust our sampling function with our W, or weight. So there are different options for changing the weight to choose from, and we'll discuss those now. So here's a diagram to depict two of the most common weighting options and how they are used. So on the left, we have natural weighting. So at the center of the array, remember at the center of the array, we have shorter baselines and there's more data points. So the further out from the center you go, the less data points you have. So in natural weighting, the weight is assigned based on the density of the visibilities. So at the center, you have more visibilities, so a heavier influence on the image. So in this case, for the image, there's a 3 because that is where the most points are located. We point to that, 3. And as you move out, the weight reduces to 2 and then to 1. The image on the right shows what uniform weighting looks like. So you can see that the points in the UV plane would be assigned the same value regardless of the location. In this case, the value is 1. In natural weighting, the low spatial frequencies are weighted up, whereas in uniform weighting, the low spatial frequencies are weighted down. As we saw in the image, during natural weighting, the central UV points, they were weighted to a 3. And then when the weighting is switched to uniform, the values were reduced to 1. So if you give more value to the outer points, you'll have better resolution, but you lose out on the impact of the large scale flux. So natural weighting is bad for resolution, but better for signal to noise, where uniform is better for resolution, but worse for signal to noise. Another popular weighting option that you can choose from is called Briggs weighting. Briggs is sometimes called robust weighting. So Briggs is a hybrid between uniform and natural weighting. So in clean, the Briggs weighting option has an additional parameter called robust. So the robust range can be set between -2 and +2. At -2, the weighting resembles a fully uniform weighting. At +2, the weighting resembles fully natural weighting. A robustness set to 0, which is in the middle of both weighting types, gives kind of the best of both worlds. So the benefit of Briggs weighting is you'll get images with better resolution, like uniform weighting, but you get better signal to noise, like natural weighting. So another option you can use to adjust your dirty beam shape is something called tapering. So tapering involves multiplying the visibilities by Gaussian in the UV plane. This is the same as convolving by a Gaussian in the image plane. So it downweights the long baselines and gives more weight to the short baselines. The result is a degraded resolution. But another problem, so you have bad resolution, but tapering can also downweight the data at long baselines, so your point source sensitivity is degraded. Well, if tapering makes the resolution and the sensitivity worse, why would anyone use it? Well, while it does degrade sensitivity and point sources, it can improve sensitivity in extended structures sampled by the short baselines. So care should be taken though, because if you tapered all of your data, then you'd have nothing to image. And if you're only interested in a large scale structure, it might be useful to taper away the small scale structure. So here I have included a summary of all the different options I've talked about and their impact on resolution, point source sensitivity, extended source sensitivity, and side lobes. So if you want point source sensitivity, you should look into natural weighting. If you want resolution, uniform or Briggs could be better. If you want to bring out extended source sensitivity, then taper may be your best option. So here is an example of a supernova remnant and how 3 different options affect the image. So in the natural weighting, it's most sensitive to extended emission. So you get dark regions which have negative values around the extended emission. So we call those negative bowls, and they occur when you have unsampled visibilities near the origin of the UV plane. So you can see those with data with long baselines and very little short baselines. So in the uniform weighting, you get the best resolution, but not as good sensitivity. So with the Briggs, which is on the far right, you get, with the robustness set to 0, gives a compromise between the natural and uniform. So you get high resolution, or better resolution and better sensitivity. So I've added another example where it shows 4 different options, this time including tapered. You can see that with a tapered weighting, your resolution is a lot worse. You have 8 arc seconds. Your best resolution is still uniform. But if you want to get a balance, it looks like robust is probably your best option again between natural and uniform. So when you clean an image in CASA, it's going to produce multiple output files. So you have your .image file, which is your final clean image. You also have your .psf, which is the point spread function or the dirty beam. Then you'll have another file called .model, which is the image of all your clean components. There's a file called .residual. So the residual will, after subtracting clean components. So you need to look, you can look at that to decide whether or not to continue to clean. And then there is a file called .flux, which is relative sensitivity on the sky. If you put PB core equals true, it divides the .image file by the .flux file. So now let's talk about confusion. Sometimes on the edge of the primary beam, you can have a very bright source that's affecting your image. So it'll cause like these ripples into the center of the field, as you can see in the bottom corner here. And there's some artifacts around your images. So the primary beam is spectrally dependent, so the image subtraction should include such corrections and be performed in full spectral line mode. So if you have pointing errors, that'll introduce gain and phase changes on the edge of the primary beam. And if severe enough, the apparent source structure will change. So how do we deal with these bright sources? In order of complexity, with the easiest being, we can set an outlier field. So with an outlier field, you can deconvolve the confusing source while imaging the field of interest. Then there is a little bit more tricky option, which is peeling. So peeling is the second option, but it requires self-calibration. And we haven't discussed self-calibration, but you will get to it in another lecture. And then there is the more difficult option, which is direction-dependent calibration. So we won't get into that today, but I will say not all telescope arrays can do direction-dependent calibration. And you might talk about it in your advanced imaging lecture. So when you're setting an outlier field in CASA, you have to assign an outlier file. So this is just an extra document that you put in that has an image name, the image size, a phase center, and a mask. And you can set, there's no limit to the number of sources you can put in the file. So if you have 10 confusing sources, you could put 10 in the file. So here's the results of the image that I showed you previously when you've used the outlier field. So when you've cleaned it, your image has improved much, much better. So peeling. So if you try to use an outlier field and nothing is working, you might need to do peeling. So after you do a phase calibration, you perform a self-calibration for the bright confusing source. You need to subtract the source model from your visibilities, and you delete the phase solutions from the previous confusing source. So you move on to the next brightest confusing source and repeat this process until all of your confusing sources have been subtracted from the image. And then you delete all the self-calibration solutions and image the central regions again. So after you've done imaging, you may need to check the quality of your image. So to do this, what you should do is calculate the theoretical noise limit of your image. So in this equation, we have the temperature of the system, the number of baselines, and you have integration time, bandwidth, and area of apertures and aperture efficiency. But you may not have an image that exactly reaches this limit. In fact, you likely won't ever reach the theoretical limit because you have many factors to increase the noise value, such as confusion, calibration errors, bad data, deconvolution, artifacts. But it's a good point to test the quality of your image. So interferometry samples Fourier components of sky brightness. You can make an image by Fourier transforming the sample visibilities into the sky brightness. Deconvolution is used to correct or attempts to correct for incomplete sampling, but it can cause issues on its own. So you can use various different parameters such as weighting, outlier fields, changing anything to try to obtain the best image possible. So there are many more options not discussed in this talk, but you may go over some of it in your advanced imaging course, and hopefully it'll help clear up more information. Thank you.